Hello everyone. Hey guys, this is your JEE educator Megha, and today I'm there to discuss with you the ionization energy. This is going to be a very interesting session. You just please stay tuned with me throughout the session so that you learn about this property and its periodic trend and the irregularity thoroughly. So here this topic has been taken from the chapter periodicity in properties, and here let me give you a quick insight that what this session is going to cover. We'll have a focus over the ionization energy. We'll see the successive ionization energy. What happens when we remove one electron, the another electron, the another electron. What are the factors that affects the ionization energy? What do you mean by the inert pair effect? And what is its role in determining the IE, that is ionization energy? What are the variations in ionization energy? Means I will be letting you know that guys, what happens when we move from left to right along a period, or what happens when we move from top to bottom along a group. Okay, and the irregularity which is being seen in the period number 2 elements, and even the irregularity which is being seen in the group number 13 and the 14 elements. You know, group number 13 is basically considered as the most disturbing group. So yes, here there is a variation in the ionization energy. So basically, if you will understand this particular point in a better way, you will be able to understand everything very easily. Okay, so here what are the factors that affects ionization energy? My whole emphasis is going to be on this particular point. Okay, so guys, let me give you a quick idea that what is ionization energy. Ionization energy can also be termed as the ionization potential, means the potential or the power which is being required to remove an electron from the outermost loosely held shell. Okay, so basically we want to remove the electron which is being loosely held by the nuclei. Okay, so whatever be the amount of energy which is being required to remove an electron from the outermost shell of an atom which is loosely held is known as the ionization energy. So basically, as the name of this ionization, the word says ions, basically we want to create ions, and this is an atomic property. This is the property of an atom. Okay, so yes guys, this is the property of an atom. So basically from atom we want to create an ion. So let me tell you a quick idea that what does it really mean. So let's say I have taken a sodium atom. Okay, please don't bother about this line. If we take a sodium atom, so what is the electronic configuration of sodium atom? It is going to be 1s2, 2s2, 2p6, and then this is going to be 3s1. So when I see for this electronic configuration, what I will found is this is the innermost shell, then we have the 2s2 2p6, and this is the outermost shell, that is the 3s1. So if I ask you bache that what is the which is the most loosely held electron, then your answer would be the 3s1, because this is very away from the nucleus. So this is the loosely held electron. So the amount of energy which is being needed to release the most loosely bonded electron. So basically first we need to identify the most loosely bonded electron, then which will definitely be available in the last shell from an isolated gaseous atom. So as I told you that this is a sodium atom, this is an atom. I have not taken any molecule like NaCl or anything like NaF something. I have taken a gaseous atom. Okay, only atom. Okay, in its ground state. Yes guys, this is a very absolute and the required thing, that the sodium atom or any other atom has to be in its gaseous state. Okay, so this is an atomic property for which the atom needs to be in its gaseous state, in its ground state, and it must be an isolated gaseous atom. So the energy which is being required to remove an electron which is loosely held by the nucleus. So basically I want to remove this particular electron, the 3s1 electron, then I will be getting a species like Na positive plus 1 electron. So there will be the loss of 1 electron, and from the sodium atom I will be getting its ion, that is the Na positive. So this is it. So here whatever be the amount of energy which is being required to get this done is known as the ionization energy. So this is that simple. Okay, so when you will look for the ionization energy, when you will look for the electronic configuration of this Na positive, this comes out to be 1s2, 2s2, 2p6. This is it. Yes, we done. So similarly, any element, or you can say any metal, whenever it is in its gaseous isolated state, okay, when we remove the first electron, this has been considered as the ionization energy 1. Okay, this will gives us the species which is M positive. Still this will remain in its gaseous state. Then we will be removing the one more electron, we will be getting M plus 2. Then again we can remove one more electron, then this will give us the M plus 3. So yes guys, we can remove successive electrons. It's not necessary that we can only remove this first electron. Now we can remove the electron which are present into the 2s2 and 2p6 orbitals. Then we can also remove the electrons which are present in the 1s2 orbitals. But what we need to know is, this is known as the successive ionization energy. Means removal of first electron, then the another electron, then the another electron. So this was the outermost electron, the most loosely held electron. Okay, so basically here when you remove the first electron, this is known as the ionization energy 1. When you remove the second electron, this is known as the ionization energy 2, ionization energy 3, and so on, so on, so on. You will be getting the ionization energy N. Now, here we need to know that why the ionization energy is increasing. Why there is a sign of increase. Why? Guys, think like that when I'm talking about M and when I'm talking about M positive. Okay, so if you're talking about the size of an atom and if you're talking about the size of an ion, so this ion is basically having a M positive. This means that if I take this as a sodium, here I'm having 11 protons and I'm having 11 electrons. But here in the case of M positive, I'm having 11 protons but only 10 electrons. So ultimately the number of electron decreases. So the more nuclear charge will be there. So effective nuclear charge increases, and because of this effective nuclear charge increases, the size decreases. Are you getting my point? Because here these are the both the species which are having the same number of protons but the number of electrons are less. So the species where we will be having the proton electron ratio greater, then that particular species will be having more Z effective, and because of more Z effective, electron gets more tightly held. Okay, so if you will look for the size of M, this will be this much bigger. If you will be looking for the size of M positive, this becomes smaller. M plus 2 more smaller, M plus 3 more smaller. Okay, so here the size is decreasing. So when the size decreases, the electrons gets more tightly held by the nucleus, and so therefore a large amount of energy is required to remove the electron from the last outermost shell or whatever the shell you are removing. So here we are saying that as the size decreases, the ionization energy jumps up. Okay, so that's how whenever you will be removing the successive electrons, the ionization energy will always be increasing and increasing. Okay, or in general we can say that ionization energy which is being required by the electron which is present in the nth shell, that is the last shell, is less as compared to that of the ionization energy which is being required by the n plus shell, that is the inner shells. Okay, so n plus 1. So n plus 1 is because if you are talking about 2, so we can say that this is 1 plus 1. If you are talking about 3, we can say that this is 2 plus 1. Okay, so n is going to be that particular number. Now what are the factors that affects the ionization energy? As of now, I just talked about the size of the atom. So if the size of the atom is bigger, then it getting smaller, then definitely the large amount of energy is being required by an atom which is smallest in size. Why? Because here the electrons are very tightly held by the nucleus. So therefore, this atom which is very small in size has high ionization energy. Okay, so as the size decreases, we can say that as the size decreases, the ionization energy increases. Okay, we can say that. So this means that here the ionization energy and the size is having the inverse relationship, right? Absolutely. So ionization energy and size is having the inverse relationship. Now, not only the ionization energy, there is one more factor which is the effective nuclear charge. Effective nuclear charge, basically what happens is, why there is a decrease in size if we are moving from period number 2, that is if we are moving from left to right, we know that here the Z effective increases and as the Z effective increases, the size decreases. So what happens? The Z effective increases, the effective nuclear charge increases. If the nucleus is becoming more powerful and it is attracting the electron more tightly, then definitely more energy is required to remove the electron. So if the Z effective increases, ionization energy also increases. This simply means that ionization energy and Z effective are directly proportional to each other. I hope you got the point. Now, the third factor that affects is the principal quantum number. Principal quantum number, basically the energy, the energy of the shells. N, the value of N. So if I am talking about, this is my nucleus, this is N is equals to 1, 2, 3, 4. This is N is equals to 1, N is equals to 2, N is equals to 3, N is equals to 4. So if I ask you, bache, that when the value of N increases. So when the value of N increases, that is, let's say the value of N is 4, then it will be easy to remove an electron or it will be difficult to remove an electron. When the value of N increases, it becomes easy to remove an electron. Means less amount of energy is required to remove an electron. Are you getting my point? Because when the value of N is 1, then this shell is very, very close to the nucleus. So this nucleus will hold the electron more tightly, when the electrons will be in N is equals to 1. So as the value of N increases, it goes away from the nucleus, and when it goes away from the nucleus, it is loosely held by the nucleus, so it becomes easy for us to remove an electron from the outermost shell. So here I can say that as the value of N increases, the ionization energy decreases. So again, what kind of relationship we have observed? That ionization energy and N is inversely proportional to each other. Great. Now let's talk about the penetration effect. What do you mean by the penetration effect? This is the effect which led the orbital to go more close to the nucleus. Okay, so this is the effect which is being shown by the orbitals. Okay, so penetration effect and the shielding effect, both are the effects of the orbitals. Okay, they are not for the N, the principal quantum number, they are not for any other thing, they are for the shapes of orbitals. So what type of shapes we have? We have S orbital, we have P orbital, we have D orbital, and we have F orbital. Okay, so when you talk about the shapes of the orbitals, you will find that the S orbital, which is very, very spherical in shape, this has a highest penetration power. Okay, yes, S orbital is intended to get more close to the nucleus. Okay, so this has highest penetration power, then the P orbital, then the D orbital, then the F orbital. F orbital is most diffused. F orbital is most diffused. It's very, very large in size, and this orbital is very, very much diffused. So this goes away from the nucleus. Okay, and this S orbital is spherical and very small in size. This has highest penetration effect. This goes more close to the nucleus. Now what happens with the penetration effect? If this orbital goes more close to the nucleus, then of course it will be very difficult for us to remove an electron from the S orbital. So that's how I can say that as the penetration effect increases, as the electron gets more close to the S orbital or more close to the nucleus, the ionization energy increases. Means more amount of energy is required to remove an electron. So ultimately we can say that ionization energy and the penetration effect are directly proportional to each other. We got the relationship. Now what do you mean by the shielding effect? Shielding effect is basically the effect which could be caused by the inner shell electrons, because of which the nuclear attraction decreases, right? Because of which the nuclear attraction decreases when the electron-electron repulsion increases in the inner shell electrons. So basically what happens is, if the inner shell electrons will be doing the maximum electron-electron repulsion and they are very strongly shielding, means they are protecting. If here this is my nucleus and this is the last electron, and in the inner shells I am having many electrons which are shielding my last electron from the effect of the nucleus. Okay, so here I have so many number of electrons and these electrons are protecting my last electron from the effect of the nucleus. If the shielding is very good, Now we need to know who do a very good shielding. Guys, again, S orbital is having a very good shielding effect, then the P orbital, then the D orbital, then the F orbital. So if S orbital is having a very strong shielding effect, so if we are talking about the s orbital and it is strongly shielding the last electron from the effect of the nucleus, then this electron is loosely held because the nucleus is having no control over the last electron because they are working as a shield. So if these inner shell electrons are working as a shield, means this nucleus has no way of control over this last electron. So this electron can be easily removed. So ionization energy will be low. So when the shielding is strong, so I can say that when the shielding effect is very strong, the removal of electron becomes easy. Means ionization energy will be lower. Okay, means less amount of energy will be required to remove an electron. But if the shielding effect becomes poor, means these electrons are not properly shielding, they are away from each other and they are not protecting the electron from the effect of a nucleus, then what will happen? This nucleus will attract the last electron towards itself more strongly, and when it attracts the electron more strongly, then what will happen? The more amount of energy is required to remove an electron. So this means that if the shielding becomes poor, if the shielding effect decreases, then electron gets tightly held, and the electron gets tightly held, more amount of energy, means the ionization energy increases. Are you getting my point? So shielding effect and the ionization energy are inversely proportional to each other, because when one increase, the other decrease. Okay, so they have an inverse relationship. Now the last is the stability of configuration. Now what do you mean by that? Guys, if I'm talking about the stability of configuration, this simply means that whenever you will be having your P3 orbital, you will be having your P6, D5 or D10 orbitals, or F7 or F14 orbitals. So they are either half filled or they are fully filled. Okay, this is half filled, this is fully filled, half filled, fully filled. Okay, so whenever we will be having such orbitals which are half filled and fully filled, so they have the same degeneracy. Okay, these are the degenerate orbitals having the same energy. Same energy means more stability. So because of this half filled and fully filled orbitals, they becomes more stable. They are extra stable, and when they are extra stable, then it becomes very difficult to remove an electron in such a way. So whenever you will be getting P3, P6, D5, D10, F7, F14, half filled or fully filled orbitals, they will be having the very high ionization energy. Okay, so I hope all these factors that affects the ionization energy is very clear to all of you. So here we can move ahead. Guys, before moving forward and looking for the irregularity or the general trend that we could see in the case of the ionization energy, there is one more thing that we need to learn, which is the inert pair effect. Okay, so basically I want to teach you about the inert pair effect, that what is this effect. So to know this inert pair effect, let us talk about the relativistic effect. So what do you mean by the relativistic effect? Relativistic means relativity, something is doing something in relationship. Okay, so basically guys, we have a different shapes of orbitals. So this relativistic effect is also a property of the shapes of orbitals, that is S, P, D or F. As I told you that S orbital has high penetration power and the F orbital is very much diffused. Okay, so this goes away from the nucleus, this goes away from the nucleus, and this goes towards nucleus. So let's say this is my nucleus, this is my nucleus, so this s orbital goes towards nucleus and the f orbital goes away from nucleus. So this is known as the relativistic effect. That is the tendency of the orbital to goes more close to the nucleus, means relativistic compression, and the orbital which goes away from the nucleus means the orbital having a tendency to expand. Okay, so when we are talking about the s orbital, so as the size of the atom increases, so basically this effect works basically works when the size of atom increases. As we go down the group, we could see that there will be the addition of new shells, the size of the atom increases because the n value increases. So as the size of the atom increases, let's say I'm talking about 1, 2, 3, 4, 5, 6, I'm talking about 6s, 4f, 5d and the 6p orbital, then what we would see? We would see that the 6s orbital here, this, when the size of the atom increases, this s orbital will show the relativistic compression. This goes more close to the nucleus. Why the 6s orbital goes more close to the nucleus? This will go more close to the nucleus because s orbital has high penetration effect. Okay, so this will intend to go more close to the nucleus, and the d and f orbitals, okay, they have a tendency, they are more diffused, so they will be showing the relativistic expansion, they will go away from the nucleus. Okay, so this is going more close to the nucleus, and they are going more away from the nucleus, they are going away from the nucleus. So when this goes close to the nucleus, this is known as relativistic compression. Relativistic compression. And when it goes away from the nucleus, the size of the atom is going to increase, so this is known as the relativistic expansion. Okay, so understood what is relativistic expansion and the relativistic compression. Now let's talk about what is inert pair effect. So basically the same example which I have taken. So let's say I'm talking about any of the species like boron, aluminium, gallium, indium and the thallium. Okay, I'm talking about the thallium. So when I have to write down the electronic configuration of thallium, this comes out to be 6s2, 4f14, 5d10 and 6p1. Okay, so this is the electronic configuration for the thallium. So here the size of the thallium is bigger because we know there is the addition of new shells, so the size of the thallium is bigger. Now size of the atom is increasing. Now here the ns orbital will show more and more relativistic compression, means this s orbital will goes more close to the nucleus. Okay, and when this goes more close to the nucleus, this pair of electron will become inert in nature. Now yes, this is the inert pair effect. So basically as the size of the atom increases, the s orbital shows relativistic compression, this goes more close to the nucleus. So ultimately if these electrons, though if you would see, you would find that we are having 4f14, we are having 5d10, then we are having 6s2 and 6p1. So if I ask you, bache, what would be the ionization energy, what would be the last shell electron that you will be removing, you would say, ma'am, 3, hai na? Because these are the 3 electrons which are present in the outermost shell, that is 6s2, just a minute, let me rub this. Yes, so what we were writing, I was writing as 4f14, 5d10 and this is 6s2 and this will be 6p1. So these are my last shell electrons which are loosely held by the nucleus, but as the size of the atom increases, this shows relativistic compression. So because the 6s orbital shows relativistic compression, here we have 2 electrons, but they are going more close to the nucleus, so it will be very, very difficult for these electrons to participate in the bond formation. So these 2 electrons will not participate in the bond formation. These 2 electrons are very, very difficult to remove, or very, very large amount of energy is required to remove these 2 electrons. So here they don't participate in the bond formation, they show poor ability. So here these are the ns2 electrons that shows poor ability of bonding. So when they will not show the ability of bonding, then they will be called as inert. They will be called as inert. Inert means noble, or you can say non-reactive. Okay, so they are not going to participate in any reaction, but relatively, yeah, only this one electron can be removed or can participate in the bond formation. So what does this mean? The f and the d orbitals are showing the relativistic expansion and the s orbital is showing the relativistic compression, and because of this reason, because of this relativistic compression, this does not participate in the bond formation, shows poor ability of bonding, and this is known as the inert pair effect. Now why we call it inert pair? As you can see that this is a pair of electron, a pair of 2 electrons. So because this is a pair of 2 electrons, this is known as inert pair effect. Okay, sometimes people confuse that this is a lone pair, but guys, no, this is not a lone pair. Okay, lone pair is the one which is freely available for the bond formation, but this is an inactive pair of electron, which is a non-bonded pair of electron and which is inactive, which cannot participate in the bond formation. Okay, so such electron pair don't cause repulsion. This even can't cause repulsion because it is being compressed towards nucleus. So we can say that this is stereochemically inactive lone pair. Okay, so this is about the relativistic effect and the inert pair effect. Okay, so these are the pair of electrons, and so therefore they are known as the inert pair effect. Now what would be the variations in the ionization energy? Okay, so after learning what is ionization energy, energy required to remove an electron from the outermost or the loosely held electron from an isolated gaseous atom in its ground state. This was the ionization energy. Looking over the factors that affects the ionization energy, like the size, Z effective, and so many factors, we come to one conclusion, that in general, when we will be moving from left to right, that is along a period, let's say if you're talking about period number 2 or period number 3, when we are moving from left to right, that is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. When the size, what happens with the size? The size decreases. When the size decreases, as the size decreases, the ionization energy increases because the electrons gets more tightly held, so more energy is required to remove an electron. So this is the thing that we would say in general. Okay, in general means in 90% of the cases, okay, the majority of the cases. So whenever we talk about a major number of cases, we use a word general. Okay, we generalize it. So when we go down the group, as we go down the group, the size of the atom increases. So the size of the atom increases, more number of shells are getting added, means the electrons, the distance between the nucleus and the electron is increasing. It becomes easy to remove an electron. So as the value of n increases, we know that the less amount of energy is required. Ionization energy decreases. So we can say that as the size increases, the ionization energy decreases. So depending upon the size, we have generalized that what happens with the ionization energy. Now, is this all okay? Or do we need to know more on this? Absolutely, we need to know more on this. Guys, this was simply a general trend. Okay, now there is lot to do. What is, let me talk on the period number 2. In the period number 2, basically what happens? Let's have a look. Lithium to beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. You would say कि when we are moving from left to right, the size decreases. If the size is decreasing, here the size is decreasing, then what should happen? This is neon. You know, in the neon there is a van der Waals radii. I discussed this thing in my previous lecture, that is on atomic radii. So please have a look on it if you don't know. So here neon, in the case of neon, there is a van der Waals radii. There is no, the neon size is not small. Okay, so when you look for the size of the atom, you would say here the size of the atom decreases. So the ionization energy has to increase. You would say that this has to increase. But in absolute terms, we found something different. Okay, so what is the difference that we have found? Let's have a look. Okay, just a minute, it is getting messy. So let us do this again. Okay, so what we have actually found is, so we found an irregularity. We found that here this beryllium and boron and this nitrogen and oxygen are showing some abnormality. And here also the neon and the fluorine. Why is it so? Let's have a look. Guys, from lithium to beryllium, you were saying ki the order has to be this, but we actually found, okay, this is 2s1, this is 2s2. Here the number of electron is getting added, but at the same time the number of proton is also increasing, right? If you would see the lithium, here we have 3 protons and the 3 electrons, 3 protons, 3 electrons, and here we have 4 protons and 4 electrons. Okay, so the number of proton is also getting added. So of course the Z effective increases, the size becomes smaller, so ionization energy has to be greater. Okay, fine, this is done. Lithium and beryllium, if you would compare, then beryllium will be having the more ionization energy. Absolutely, this is fine to say. Okay, now let us look for the another molecule. If we compare between the beryllium and boron, So guys, when we compare between the beryllium and boron, there was one thing, because whenever we remove electron we have to see that from which orbital we are removing electron. So here we are removing electron from the 2s2 orbital, and here we are removing electron from the 2p1 orbital. They are 2 and 2, the value of n is same, but here the orbital is s and here the orbital is p. So is it easy to remove an electron from the s orbital, or is it easy to remove an electron from the p orbital? What would be your answer? If there is a change in orbitals, then guys, it's always easy to remove an electron from the p orbital, because s orbital shows more penetration effect. It has a tendency to go more close to the nucleus. So because here the penetration effect dominates, s orbital has more penetration effect than the p orbital. S orbital has more penetration effect than the p orbital, and because of this certain reason, what will happen? The ionization energy of beryllium will be greater than that of the boron, because more energy is required to remove an electron from beryllium rather than boron. So this is an important case. Okay, so here please remember, beryllium ionization energy is greater than boron, and this is a question which could be asked maximum number of times in your JEE paper. Okay, so here is the reason. So why only look for only one single factor, that is size? There are so many factors, guys, so we need to consider all of them. Okay, so being a JEE aspirant, this is a difference that you have to build. Now let's have a comparison between the boron and oxygen. So this is 2p1, this is 2p1, 2p. Okay, fine. One electron, two electron means one electron is getting added up and the one proton is also getting added up. So no other change. Absolutely, we could say the Z effective increases, the size decreases, and when the size decreases, more amount of energy is required. Okay, it was a simple general trend. No issues with that. Now what about the carbon and nitrogen? Okay, please don't confuse, this is carbon. Okay, or let me remove this circle. I just made it as a size now. So okay, so when I'm talking about the carbon and nitrogen, here this is 2p2 and here this is 2p3. So you know, in the p orbital we have the three subshells, and this is 1, 2, 3, and this is half filled configuration. And when you are having any kind of half filled and the fully filled configuration, we have seen, no, in the case of the factors that affects the ionization energy, that whenever we will be having the half filled or the fully filled configurations, then there will be more stability. So this is the case here. So what we would say, that the half filled and the fully filled configurations are going to be the more stable. So ultimately, when the nitrogen configuration is more stable, it requires more amount of energy to remove an electron. So definitely nitrogen will be having more ionization energy as compared to that of the carbon. Now when we compare between the nitrogen and oxygen, then what happens? Look for the electronic configuration. This is 2s2 2p3. So here, and this is 2s2 2p4. So if you would look for these two orbitals, 2s2 2p3 and 2s2 2p4, what you would compare? This is p3, which is again half filled, and this is p4. So here we have a repulsion of electrons. See, this is something like this, 1, 2, 3 and 4. So there we are, this fourth electron is actually undergoing repulsion. Okay, because electron and electron, they are the like charges, and they will try to repel when they will be filled in the same subshell. Okay, so there we will be having a repulsion, so less amount of energy is required to remove an electron from the oxygen. But here in the case of nitrogen, this is the half filled configuration, which is extra stable. So if it is extra stable, more amount of energy is required. So when you compare between the nitrogen and oxygen, in the case of nitrogen, more ionization energy is required as compared to that of the oxygen. So this is the case that we need to know. Okay, now let's have a look over the oxygen and fluorine. Oxygen and fluorine, this is 2p4, 2p5. Okay, fine, the same p orbital, no extra factor, no penetration effect, no shielding effect, no stability of configuration, nothing else, है ना? So only Z effective is dominating. So only Z effective increases, the size decreases. Size decreases means ionization energy increases. So here we could easily say the ionization energy of fluorine is greater than that of the oxygen. Now here comes the last and the most important scenario. If you compare between the fluorine and neon, now guys, you know, you would say, ma'am, neon size is bigger, this will require less ionization energy. No, please don't do this kind of bullshit. here you please focus over the don't you really think that size is a more dominating factor here? No, the size is not a most dominating factor here. The point is neon. This is neon. This is neon, and neon is having the 2p6 kind of configuration. This is a noble gas which is having the inert. They are also known as the inert gases. They are non-reactive. They don't even react. Okay, they have the most stable configurations. They are 2p6. So when all the electrons are paired and the electrons are completely filled, these are the degenerate orbitals of same energies. They are extra stable. So ultimately guys, very large amount of energy is required to remove an electron from the neon, and even you can't even found any compound of neon, because neon's electron don't even participate in the bond formation. This is this much inert in nature. Okay, so here highest amount of ionization energy is required. We could say more. So don't go over its size. Okay, so here which factor dominates? Here the stability factor dominates. So basically whenever we get a question, we have to compare it thoroughly. Okay guys, if you would say ki ma'am, in the case of s orbital, do we have half filled or fully filled concept? No guys, S orbitals are basically spherical in shape. Spherical means sphere, just like a ball. Okay, just in the case of a ball, the gas is equally distributed throughout the ball. The similar way, the electrons are thoroughly distributed in the S orbital. Okay, so here there is no concept of half filled or fully filled. If one electron is there or two electrons are there, they have the same stability. Okay, the half filled and the fully filled configurations are only for the p orbital, for the d orbital, and for the f orbital. Okay, when this is p3 or this is p6, when this is d5 or d10, or when this is f7 or f14. What's the reason? Because the p orbital is not spherical. Here the electrons are not equally distributed. The p orbital is dumbbell shaped, so the electron could either be here or either could be here. Okay, so in the p orbital, the electrons are not equally distributed. It has a node. Okay, so that's why the stability factor comes for the pdf orbital, not for the s orbital. So ultimately we have come to this particular conclusion that the lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, nitrogen is going to be the most having the high ionization energy as compared to that of the carbon and oxygen both, and here the beryllium is going to be having the more ionization energy because of the more penetration effect caused by the s orbital. Okay, so here the order will become this, and here the order will become this. Okay, so whatever the way, this is also right and this is also right. Okay, so both the way you can write it. So depending upon that, what question comes in your paper. Now we have done with the irregularity which could be seen in the period number 2 elements. Now there is one more irregularity that we have to focus, that could be seen in the group number 13 and the 14. Matlab, I majorly say group number 13. Okay, group number 13 elements. So basically what happens is, if we will be talking about the boron, aluminium, gallium, indium and thallium. So first of all, let us write down their electronic configuration. This is 2s2 2p1, this is 3s2 3p1, this is 4s2 4p1. So when I will be writing 4s2 4p1, I must also write 3d10. Okay, so here in the case of the gallium, we have filled 3d orbital. Just a second, we have a, yes, all good. So we have a filled 3d10 electrons. Okay, then this is going to be the 4d10 5s2 5p1, and then this is going to be the 4f14 5d10 6s2 and 6p1. Okay, so if you have watched my atomic radii lecture, then you probably know we found that because of this d10 electrons, because of these 10d electrons, there was a poor shielding, and because of that poor shielding, there was a scandite contraction. The nucleus will be able to attract the electron more tightly, and because of this reason, we found that the boron size is this much, the aluminium size increases, but then after, the size has to increase as the number of shells are increasing, but we found that the gallium becomes smaller in size. The reason being, The reason being poor shielding caused by the 3d orbital. Okay, the size decreases, and then after the indium the size increases, and in the case of thallium we expect the size has to increase. But what we again found? We again found that in the case of the thallium there is a poor shielding by the f orbital, the 14f orbital, and because of this poor shielding the nucleus attract the last electron, and so therefore the size of thallium and indium becomes almost the same. So this becomes the same. Okay, now here the question is not about the atomic size, here the question is about the ionization energy. Okay, so guys, in general you say कि as the value of n increases, the ionization energy decreases, means less amount of energy is required to remove an electron because the electrons are getting away from the nucleus. But here comes the ambiguity. Ambiguity means here comes the irregularity. What is in the case of the gallium? What has happened in the case of a gallium? We found that because of this candide contraction, the gallium size is abnormally small. So when the gallium size is abnormally small, if the size of the gallium is getting smaller, and so therefore the electrons are getting more tightly held, so ultimately the ionization energy of gallium is higher. The ionization energy of gallium is higher. Okay, so the ionization energy, so gallium will be having more ionization energy as that of the aluminium. We can say that if the comparison is for the ionization energy, then we would say that gallium is having more ionization energy as compared to that of the aluminium. You would say gallium must have low because the n value increases, but no, because of this candide contraction the electrons are getting more tightly held, the size is getting smaller, so more amount of energy is being required by the gallium. Okay, now what comes with the thallium? Now here this happens, that is the lengthened contraction, the poor shielding by the 4f14 electrons, and because of this reason the electrons are getting more tightly held. Now here there is a more electron density, right? Indium and thallium, they both are having the same sizes, but the thallium is having more electron density, electrons are more tightly held. So because of this reason thallium will be having more ionization energy as that of the indium. So we can also say that thallium is having more ionization energy than that of the indium. Okay, because of the lengthened contraction. I hope you got the point. So basically whenever there will be poor shielding because of the 3d or the 4f electrons, then this increases the Z effective. If there will be the poor shielding by the inertial electrons, the nucleus will be able to attract the last electron more strongly. Okay, so this is what happens. So here the Z effective increases, and so therefore ionization energy increases. More energy is required to remove an electron. Now here, if someone asks you what is the correct order, then we found that the gallium and the thallium, they both were very irregular in their trend. Okay, so what is the exact trend if we want to know? Guys, the boron, because the boron is absolutely, because this is of the second shell, so the second shell is very close to the nucleus, and so therefore boron is having the highest ionization energy. But then after comes your thallium. Yes, absolutely, you would be surprised to see, but yes, the thallium is having the ionization energy. Then after thallium, because they were abnormal, no, they both were abnormal, and then after comes the gallium, and after gallium we all know कि after the gallium and aluminium, the aluminium will be having the less ionization energy, and the very less ionization energy can be required by the indium. Okay, so indium comes here, so the very less amount of ionization energy is being required by the indium. I hope you got the point. Why boron is having the highest? Because this is of the second shell, smallest in size. Okay, if you would compare all the sizes, yes, boron is very small, that's the reason. Then here comes the thallium. Okay, so this order you need to remember, that what actually happens. So basically you need to know two things. Yeah, gallium and thallium, because of this candide and the lengthened contraction, they are smaller, and so therefore they will be having abnormally high ionization energies. Okay, let's move forward with the group number 14 elements. If I will be focusing over the group number 14 elements, guys, let me tell you, here also we have the carbon. You would say, ma'am, we do have 2s2 2p2, we have 3s2 3p2, we have 3d10 4s2 4p2, we have 4d10 5s2, 5p2, and here we have 6 sorry, we have 4f14, 5d10, 6s2, 6p2. Okay, so this is I think I did something wrong. No, it's all fine. Enough, good enough. So you would say, ma'am, here also we will be having a d orbital and here we have the f orbital. So there also we will be having the scandite and the lengthened contraction. Then guys, let me tell you one thing. The scandite contraction is going to be till gallium only. Okay, not after that. So basically, if I show you one of my previous slide, if I show you one of the previous slide, here you please focus that the gallium, if you're talking about this particular series, because of this particular D10, 1 to 10, D1 to 10 electrons, there will be poor shielding and they are going to affect only gallium. Okay, the impact will not be over the germanium or arsenic or selenium, only gallium will get affected. And here in the case of the period number 6, if you will be talking about the poor shielding by the 14f electrons, so these are basically our 14f electrons which are doing a poor shielding. So the effect of poor shielding by the 14 4f electron is over the hafnium, tantalum, tungsten, okay, Re, Os, Ir, Pt, Au, Hg, thallium, Pb and Bi. So the impact will be seen till here. Okay, so means the scandite contraction is going to impact only gallium, but the lengthenoid contraction is going to impact all the other elements just after the lengthenoid series. So that's how lengthenoid contraction is a very, very major contributor. Okay, so the effect of lengthenoid contraction. So if we are talking about the group number 14, in the group number 14, which element is going to be disturbed? Only the lead. Only the lead is going to be disturbed, rest will not get disturbed. Okay, because here they are not disturbing and only the lengthenoid series is disturbing the lead. So here let's move back to that particular thing and let's have a look at what happens in the case of group number 14. So only the impact can be caused over the lead. Sorry. Okay, can be seen over the lead. Okay, so here we could say that the ionization energy will be highest for the carbon, of course. Second, shell very close to the nucleus, so more energy is required to remove an electron. Then as compared to that of the silicon, then the germanium, then Sn must be, but here we found that in the Pb there will be the poor shielding by the 4f electrons. Then the nucleus will hold the electron more tightly. So ultimately when the electrons are more tightly held, here we have the lengthened contraction. So its ionization energy will be greater than that of the Sn. Okay, so here the thallium goes till there, but the Pp will remain there. Okay, so here we could say that the group number 13, majorly group number 13 is the most disturbing group. It has maximum abnormalities, abnormality in size, abnormality in ionization energy. Okay, so these are the two things, that is the lengthened and the scandite contraction, every student must know. Okay, so here guys, let us see. Okay, we have looked for the for the period number 2, we have looked for the disturbing groups like group number 13, group number 14. I told you about the noble gases. What happens in the case of noble gases? They are extremely inert, so no matter what size they have, the ionization energy is going to be the highest for them. Now let us have a look over the group number 1. It's very easy, very easy. Only one thing I want to tell you, lithium, sodium, potassium, rubidium, cesium and francium. Okay, so first of all, this comes in period number 2, 3s1, 4s1, 5s1, 6s1. So first of all guys, francium is not an S block element. Okay, so if you compare this particular series, then please compare it till cesium. Okay, because it's very required, because they are the S block elements, they are the alkali metals. Francium is a radioactive element, so francium is radioactive in nature. Francium is radioactive in nature. So if you are talking about the size, lithium is smaller, then sodium becomes larger and largest. So cesium is of largest size. The size of the cesium is highest. Okay, so this is the largest species. So when the size of the cesium is largest, its ionization energy is going to be very low. Okay, so cesium has the lowest ionization energy, and this is the most important fact among all the periodic elements, that cesium is the species, Cs is the species having the lowest ionization energy. Sorry, you please correct it, guys. Lowest, I really don't know why is this so happening, but I would say you please be tolerate, please tolerate this thing with me. Okay, cesium, that is the lowest ionization energy. Okay, so guys, we could say that here when you are moving from top to bottom, that is from lithium to francium, the size increasing, so therefore the ionization energy decreases. Okay, so decreases, you would say the francium will be having the lowest ionization energy. You would expect that, this must be your expectation, that francium would be having the lowest ionization energy because it is largest in size. But no, guys, but no, francium will not be having the lowest ionization energy. Cesium will be having the lowest ionization energy. Francium is an extremely unstable element because this is the radioactive in nature. Okay, so we won't consider francium. I hope the point is very clear. So we can say that Li, Na, K, Rab, Li, Na, K, Rb, Fr and Cl. Cesium is having the lowest ionization energy. Okay, not francium. Francium is radioactive, so this is extremely unstable. Now we are all done with the ionization energies. Okay, I told you about every regularity and everything has been just covered. Okay, so now this is just an example to make you understand the successive ionization energy, that how the things works. So guys, if you will look for the sodium atom, this is 1s2, 2s2, 2p6 and 3s1. So first of all, if you are talking about the first ionization energy, that is the removal of first electron, you will be getting 2p6, 1s2, 2s2, 1s2, 2s2 and 2p6. Okay, then you are removing another electron. This is known as the ionization energy 2, and this will give you the 2p5. So if you would see the ionization energy 1 and ionization energy 2, the ionization energy 1 is going to be very less than the ionization energy 2. So why is this so? The reason being, here the Na positive has got the stable noble gas configuration. So here you will be getting a big jump in the ionization energy. Why there is a big jump? Because of the stable noble gas configuration. Okay, so whenever we have a valence shell electron, these valence shell electrons are very easy to remove. Okay, if any species is having 10 number of electrons, yeah, you can remove 10 electrons. You will be having ionization energy 1 to 10. But I am talking about a big jump. So whenever there will be the valence shell electrons are very easy to remove, but after that, once you reach the stable noble gas configuration, the ionization energy becomes very high. That's how I am saying that the ionization energy 2, IE2, for this Na positive is very higher than that of the IE1. Okay, I hope you got my point. Then I can remove one more electron. This will be IE3 and will give you Na positive and 2p4. So this way you can remove n number of electrons. Similarly, you can do for the magnesium. This is 3s2. You have removed one electron, IE1 for magnesium. You have removed another electron, IE2 for magnesium. Absolutely, IE1 is going to be less than the IE2. Why? Because the first electron, the removal of first electron is always easier, because when this becomes Mg positive, the size of the atom decreases. This is the cationic species, and if you have studied the ionic size, then you definitely know the size of Mg positive is smaller because more protons and less electrons, so high effective, Z effective. So size decreases. So when the size decreases, the ionization energy increases. Absolutely. So when you remove one more electron, it becomes 2p6. Okay, that is the ionization energy 2 we are talking on. Okay, but since you will be removing one more electron, that is the ionization energy 3, now you are removing electron from the 2p6 configuration, which is extremely stable, extremely inert. So here you will be getting a big jump in the case of the ionization energy 3. I'm so fed up with this pen. I really don't know why is this working like this. So basically I hope you got the point. I was trying to make a point that the IE1 is less than that of the IE2. The ionization energy is increasing, but if you are talking about the ionization energy 3, the energy is going to be a very high. So here we will be getting a big jump. So this big jump, I hope you understood that what's the reason behind it. Okay, you could also be getting the questions like for the JEE, you will also be getting some questions like what happens, what is the comparison between the IE1 of this and this. Okay, let me remove it. Yes, okay. So now let's have a look that what happens in the case of the ionization, the first ionization energy for the sodium and the first ionization energy for the magnesium. Here you were removing the last electron, which is very easy to remove than that of the magnesium. If you would compare, the sodium is larger in size as that of the magnesium, so of course its ionization energy is going to be less than that of the magnesium. The question could ask you, compare the second ionization energy of sodium and compare the second ionization energy of magnesium. Guys, here in the case of the IE2 of sodium, you are removing an electron from the stable configuration, right? But here you are not removing electron from the stable configuration, so IE2 for sodium will be greater than that of the magnesium. If you're talking about IE3, similarly you can compare, you are removing electron from 2p5, which is quite easy, but removing electron from 2p6 configuration is very difficult. This is stable fully filled configuration, so the ionization energy 3 for the magnesium will be higher. Okay, now similarly you can do for the IE4 for the sodium and magnesium. So this is it. An element can have many ionization energies as the number of electrons present in it. Whatever be the number of electrons, that could be the number of ionization energies, but whenever the valence shell electrons gets loosed, you will be getting a big jump in the ionization energies. Okay, so this is it. I hope you understood the point. So guys, the last part is whenever you need to find out the as per the quantum mechanics, whenever you need to find out the ionization energy for any hydrogen like system, I mean to say one electron system. Hydrogen is having only one zero proton and even one electron. Okay, sorry what I'm saying, zero neutron and only one proton and one electron. Okay, so when I'm talking about the one electron system like He positive, Li2 positive or Be plus 3, for such species, for the such one electron species, we could have the ionization energy can also be calculated by this formula which you might have studied in the chapter atomic structure, 13.6 into Z square by N square electron volt per atom. And for the multi-electron system, if you need to find the same, you just replace this Z by Z effective, because here when there is a multi-electron system, there will be the shielding effect, there will be the penetration effect. So ultimately we know that the Z effective is equals to Z minus sigma. So just subtract the shielding effect. Okay, if there is a strong shielding, then what will happen? The Z minus sigma will become a small value, that is the Z effective decreases. Okay, so the shielding actually affects. So when you have a multi-electron system, because in the multi-electron system only the shielding effect works. Shielding is a property in the multi-electron system. Okay, so you can calculate it by this formula. So simple, you just put the values of Z effective, they might be given to you in the paper, and N is the number of shell that in which the electron is present. This is it. If you put the value, you will be getting your answer. So yeah, this is all about. So here we do have the properties of ionization energy, that what is the application of ionization energy, how the ionization energy affects the other factors like metallic character or the reactivity of metals or the reducing power of elements, which I will be discussing with you in one of my another lecture. So thank you so much guys. I hope you learned this particular topic, the ionization energy, and you enjoyed the session well. So if is it really so, then thank you so much. I would be very happy if this lecture brings a smile over your face. So guys, please like, subscribe and share, because this is only the way you will be able to express your feelings, your emotions towards my lecture, and your effort of you, whatever the step that you took to either like or subscribe the channel or sharing this video will definitely motivates me and helped me to build, to create more engaging and more explanatory sessions for you guys. So thank you so much for you all. You do follow me on Unacademy for my plus lectures for the IIT JEE category. And guys, here is my profile, so you please don't forget to follow me here. This is it. Thank you. Let's crack it. Be ready for my next video, which is going to be released very soon.